This is the tutorial for network layer control plane. The network layer control plane is a part of the networking architecture responsible for managing and controlling network traffic at the network layer. DHCP is a critical component of the network control plane, used to assign IP addresses and other network configuration parameters to devices on a network. Network address translation, also known as NAT, is another important technology that operates at the network layer, allowing multiple devices to share a single IP address and provide a measure of security. Routing algorithms are also a key aspect of the network layer control plane, determining the best path for a data packet to travel between network devices. The Internet Control Message Protocol, or the ICMP, is used to manage error messages and control messages related to network traffic. The DHCP, Dynamic Host Configuration Protocol, is a network protocol that simplifies the process of assigning IP addresses and other network configuration parameters to devices on a network. It automates the process of IP address assignment by centralizing it on a DHCP server, which manages a pool of IP addresses that can be dynamically assigned to devices on the network. When a device joins a network, it sends a DHCP discover message, which is a broadcast message that requests an IP address assignment from the DHCP server. The DHCP responds with a DHCP offer message that includes an available IP address, subnet mask, default gateway, and DNS server IP addresses. The device can then accept the offered IP address by sending the DHCP request message to the server. Finally, the DHCP server responds with a DHCP path message that confirms the IP address assignment and other configuration information. It also offers several advantages over the manual IP address configuration that includes the automated IP address assignment, and it simplifies the process of IP address assignment by centralizing it on the DHC server as it has been discussed before. And the efficient use of IP addresses is also enabled by the DHCP, as it only assigns them to devices that need them and reclaiming them when devices leave the network. It reduces the risk of IP address conflicts and enables better use of limited IP address resources. Simplified network administration is also possible due to the DHCP, as it simplifies network administration by eliminating the need for manual IP address configuration, and it reduces the risk of configuration errors and enables centralized management of network configuration parameters. DHCP is used in many type of networks, including local area networks, wide area networks, and the internet, and can be configured to support different types of IP address assignment that includes dynamic, static, and reserved IP addresses. It is an essential protocol for management of IP address and the other network configuration parameters on a network, and it simplifies network administration, reduces the risk of configuration errors, and enables efficient use of IP addresses. NAT (Network Address Translation) provides IP address translation functionality by modifying the IP address of packets as they pass through a uh, network device. When a device on a local network sends packets to a destination on the internet, the NAT device replaces the private IP address of the source device with the public IP address of the NAT device. When the response packet is sent back to the NAT device, it modifies the destination IP address to the private IP address of the device that originally sent the packet. It can also perform port translation that allows multiple devices on a local network to share a single public IP address. And it provides IP address translation functionality by modifying the source and destination IP addresses of the packets as they go through a network device, and allows the devices on a local network to communicate with the devices on the internet using a single public IP address. There is replacing of the source IP and port of the outgoing datagram, and remote client responds with the NAT IP and port as the address of the destination and remembers it in the NAT translation table. The incoming datagram replaces NAT IP with the source IP, etc. NAT router then changes the datagram address of the source and updates the table. and the NAT translation table is a data structure used by the NAT device to keep track of the mapping between the private IP address and the public IP address and the port numbers. It stores information about the connection being translated, such as private IP address and port number and public IP address, and a port number and protocol type. It can also be used for troubleshooting network connectivity issues. It operates on the IP version 4, but now IP version 6 has also arrived. Routing algorithms. The network layer is responsible for packet forwarding and routing packets in the TCP/IP protocol. The control plane operation in the network layer consists of two ways: the per router control, which is a traditional way, and the logically centralized way. In the per router control plane architecture, each router runs its own routing protocol and communicates with the nearby routers to exchange routing information and maintain the routing tables. But this architecture can become complex and difficult to manage when large scale networks are there, and that leads to scalability and performance issues. On the other hand, the SDN control plane provides a centralized view of the network, making a network management and troubleshooting much easier. Routing protocols play a crucial role in deciding the paths that are good via the network of routes for the packets from host to destination. So a good route is one which is fast, least costly and least congested, and which is difficult to identify and secure. The network is represented as a graph with nodes and edges where the cost of each edge is determined and is inversely proportional to the congestion. The aim of algorithms is to find the least cost of network. Centralized algorithms find paths with least cost, such as the link state algorithm, while the decentralized algorithms calculate in an iterative manner, such as the distance vector algorithm. Load sensitive algorithms change dynamically to reflect the level of congestion on the link, while insensitive ones do not. Routing algorithm can be classified based on what information they require to determine the best route. So there are two types of routing algorithms: linked state algorithm and decentralized algorithms. The linked state algorithms have global state information about connectivity and the cost of all links in the network, while the decentralized algorithms do not require global state information about connectivity and cost of all the links in the network at the beginning. The OSPF is a popular routing protocol used in the computer networks and is built on the Digitastra's algorithm. Learning Digitastra's algorithm and the OSPF protocol requires some mathematical formulation. The distance vector algorithm calculates the shortest path from one router to another. It is a asynchronous and iterative algorithm where one has to wait for a node, recompute the distance vector, and notify the changes to the neighbors. Autonomous systems, inter-autonomous system routing, and intra-autonomous system routings are all important routing protocols used to ensure the shortest, best route for a given network. And in order to solve these problems, they are organized into groups, with the autonomous system being the most common as it is maintained by the ISP or the other ISPs. There are two types of routing protocols, the IaaS and ISPF, which work together to ensure that all routers within an AS run the same routing algorithm. The ICMP, Internet Control Message Protocol, is a protocol that is used to communicate error messages and operational information about the network to the center. It is an important part of the TCP/IP protocol suite and operates at the network layer of the TCP/IP model. ICMP is used by network devices such as routers, firewalls, and hosts to communicate status and error message about the network connectivity and other issues. The ICMP messages are encapsulated within the IP datagrams and are then sent back to the source of the original packet to provide feedback about the network status. And these messages contain a type field, a code field, which provide information about the specific issues encountered. There are various types of ICMP message, including error messages, query messages, and redirect messages. So some of the common ICMP common uses of ICMP include ping, trace route, path MTU discovery, and the ICMP can also be used for malicious purposes such as the denial of services attacks or the network reconnaissance. For example, an attacker may flood a target host with ICMP echo request messages, such as also known as ping flood. causing the target to become unresponsive to legitimate traffic. This is a tutorial on data link layer. The data link layer is the second layer in the TCP/IP protocol stack, and it follows the physical layer. It is responsible for transmitting data packets over the physical layer, and it ensures that they are delivered correctly. It is divided into two sublayers, which is the media access control or MAC and the logical link layer or the LLC. MAC layer is responsible for controlling access to the physical network media and is specified to the type of physical network being used. The LLC layer provides a common interface to the network layer regardless of the type of physical network being used. Data link layer provides several services to the network layer, including framing, addressing and error detection and correction. Framing involves breaking up the data to be transmitted into manageable frames, each with its own header and trailer. Addressing services allow packets to be delivered to the correct destination. Error detection and correction is also an important function of the data link layer, as a CRC code in the trailer is used to detect errors in transmission. In some cases, the data link layer may also provide error correction services to correct errors in transmission. The MAC protocol, Media Access Control Protocol, is responsible for enabling communication between the devices on the same physical network segment. It defines the rules for how the devices access the network media and how they send and receive data frames. It uses unique identifier called a MAC address to identify each device on the network, and the MAC address is a 48-bit hexadecimal number that is assigned to the network interface card or the NIC of the device by the manufacturer. The first 24 bits of the MAC address, called the Organizationally Unique Identifier or the OUI, identify the manufacturer of the NIC, while the remaining 24 bits are assigned to the manufacturer to uniquely identify each NIC. The MAC protocol uses two main methods for transmitting data frames, which is carrier sense multiple access with collision detection or the CSMA/CD, and carrier sense multiple access with collision avoidance, which is a CSMA/CA. In CSMA/CD, devices listen for other devices on the network before transmitting data frames. If a device detects that the network is free, it can start transmitting. If two devices transmit at the same time and collision occurs, both devices stop transmitting and wait for a random period of time before attempting to transmit again. In the CSSMA/CA, devices use a request to send or the RTS and clear to send or the CTS mechanism to avoid any collisions. Before transmitting a data frame, a device sends an RTS frame to the receiving device and asks for permission to transmit. The receiving device responds with a CTS frame to grant permission to transmit. Other devices on the network can hear the RTS and CTS frames and know to wait until transmission is complete. The MAC protocol also includes error detection mechanism to ensure the integrity of the data being transmitted. The most commonly used error detection method is the cyclic redundancy check, which adds a checksum to the data frame that can be used to detect errors. MAC address is a unique identifier assigned to a network interface controllers or the NIC for use as a network address in communications within a network segment. It is assigned by the manufacturer of the NIC and is stored in the hardware of the device and is a 48-bit address and is divided into two parts. The first 24 bits identify the manufacturer NIC and the remaining 25 bits are assigned by the manufacturer and serve as a unique identifier of the device. In a network, each device has a unique MAC address and is used to identify it at the data link layer. When a device wants to send a message to another device on the same network segment, it includes the destination MAC address in the data frame. The data frame is then transmitted over the network to the destination device, which uses the MAC address to receive the message. The data link layer is responsible for transmitting data frames between the devices on the same network segment. In order to accomplish this, the data link layer uses a protocol called the Media Access Control Protocol, which has been discussed before, which specifies how devices share the network medium and avoid data collision. The most common MAC protocol used in Ethernet network is carrier sense multiple access with collision detection, which allows devices to listen for activity on the network and transmit data only when the network is quiet. The ARP Address Resolution Protocol is used in data link layer of the TCP/IP model to map a IP address to a physical address such as the MAC address and allows for devices on a network to communicate with each other using the physical address rather than the IP address, which is necessary for data transfer on the data link layer. When a device wants to send data to another device on a network, it requires the MAC address of the recipient. To find this information, the device sends out an ARP request packet to the network. This request includes the IP address of the device the sender wants to communicate with. The ARP request packet is broadcasted to all devices on the network, and the device with the matching IP address sends back an ARP reply pack containing its MAC address. So once the sender receives the ARP reply packet, it can then use the MAC address to send data to the recipient. Additionally, the sender stores the MAC address in its ARP cache to speed up future communication with the same recipient. It is a simple and efficient protocol that helps devices on a network communicate with each other. But it is vulnerable to ARP spoofing attacks, where an attacker can send a false ARP message to associate its MAC address with the IP address of another device on the network, and it can be used for intercepting and modifying the data packets intended for the victim device. So, to prevent these type of attacks, network administrators can use measures such as static ARP address, ARP monitoring tools, or ARP implementing secure ARP protocols like secure ARP or ARP inspection. Error detection in data link layer is an important part for ensuring the integrity of the data transmission between the two network devices. There are several error detection techniques employed in the data link layer, including parity check, cyclic redundancy check, and checksum. Parity check involves adding an additional bit to each transmitted character to make the total number of ones in the character and the parity bit even or odd. The receiver checks the parity bit and determines whether any errors occurred during transmission. This technique is simple and efficient for detecting single bit errors, but it cannot detect multiple errors. So CRC is a more sophisticated error detection technique that uses polynomial division to generate a checksum for each transmitted frame. The checksum is calculated based on the data in the frame and appended on the end of the frame. The receiver then performs the same calculation and compares the checksum with the one received with the frame. If the two checksums do not match, the receiver knows that the errors have occurred during the transmission, and it can detect common types of errors, including multiple bit errors. It is a simpler error. Checksum is a simpler error detection technique that involves adding up binary values of all the characters in the frame and computing the ones complement of the result. The checksum is then appended to the end of the frame. The receiver performs the same calculation and compares the checksum with the one received with the frame. If the two checksums do not match, the receiver knows that the errors have occurred during the transmission. Checksum is less reliable than the CRC for error detection, but it is faster and requires less computational power. This is a tutorial for physical layer. It is the lowest layer in the TCP/IP protocol stack and deals with the transmitting and receiving binary data in the form of signals across physical channels. The key function of the physical layer is to transform data into signals that can be transmitted through the physical medium. Signals can be analog or digital, depending upon the type of data that is being transmitted. Analog signals are continuous and periodic, while the digital signals are discrete and non periodic. Every device in a computer network has a physical layer that allows it to send and receive signals. Physical layer devices are responsible for transmitting and receiving signals and regenerating signals that deteriorate during the transmission by a medium or a link before they reach the receiver. Repeaters are one of the examples of physical layer devices used in networks. Since physical layer is the lowest layer in the TCP/IP protocol stack, it is responsible for converting the data received from link layer into signals that can be transmitted across physical channels. The physical layer works closely with the link layer to ensure that the data is transmitted accurately and efficiently. Hubs, switches, and routers. Hubs are devices that operate at the physical layer and are used to connect multiple devices together in a local area network. A hub receives a signal from one device and broadcasts it to all the other devices connected to it, regardless of the destination. Hubs are inexpensive but not very efficient, as they often lead to network congestion and collision. Switches, on the other hand, operate at the data link layer and are used to connect devices in a LAN. So, unlike hubs, switches have the capability to learn which devices are connected to each of its port and forward traffic to only the appropriate device. This increases the efficiency of the network and reduces the chances of network congestion and collision. Routers operate at the network layer of the TCP/IP model and are used for connecting different networks together and are responsible for forwarding data packets from one network to another based on the destination IP addresses. Routers are used for routing tables. Routing routers use the routing tables for determining the best path for data packets to reach their destination. At the physical layer, switches and routers both use physical media such as the Ethernet cables, fiber optics, or wireless signals to transmit data packets. They also use a protocol such as Ethernet, Wi-Fi, and TCP/IP to ensure reliable and efficient communication. Signals. In the physical layer, signals are used to transmit data over a physical medium such as copper wire, fiber optic cable, or wireless channels, and they are electrical, magnetic, or electromagnetic representations of data that are transmitted from the sender to receiver. There are two types: analog and digital signals. Analog signals are continuous and vary smoothly over time, whereas digital signals are discrete and can only take on a limited number of values at a specified point in time. Analog signals are typically used for voice communication, where the sound waves are converted into electrical signals that are transmitted over phone line or wireless network. Digital signals, on the other hand, are used for data communication, where the data is represented in binary and transmitted over a physical medium. So, in order to transmit signals over physical medium, they must be modulated onto a carrier wave. Modulation is the process of modifying a carrier signal to carry information by varying its amplitude, frequency, or phase. There are several modulation techniques used in communication system that includes amplitude modulation, AM frequency modulation (FM), and phase modulation (PM). Each technique has its own set of advantages and disadvantages, and that depends upon the application. So, in addition to the modulation, other factors that can affect the signal transmission are noise, attenuation, and interference. So, noise is any unwanted electrical signal that can distort or disrupt the original signal. Attenuation is a reduction in signal strength as it travels over a physical medium. Interference is any electrical signal that can interfere with the original signal, such as the electromagnetic interference (EMI) or the radio frequency interference (RFI). LTE is a wireless communication standard that was developed to provide high-speed data connectivity for mobile devices. So it is a 4G technology that is widely used by mobile network operators around the world, and it is based upon packet switched network architecture where data is transmitted packets between the mobile device and network. It uses orthogonal frequency division, multiple access or the OFDMA, and multiple input, multiple output technologies, which is MIMO, to achieve a high-speed data transfer rate. The LTE network uses a variety of network components to provide seamless data connectivity for mobile devices, such as serving gateway, mobile management entity, and home subscriber server. The SWG, or uh, or the serving gateway, manages data packets routing between the mobile devices and the core network, while the mobile management entity performs tasks such as authentication, security, and position tracking. The home subscriber server is responsible for authenticating the mobile device and granting the access to the LTE. The serving gateway movement, the SWG, MME, and the home subscriber server are important components of the long-term evolution of the LTE network, which operates at the physical layer of the protocol stack. The SWG acts as a bridge between the evolved Universal Terrestrial Radio Access Network, or the UTRNA, and the core network. and it is responsible for routing data packets between the user equipment UE and the core network. The MME is responsible for managing the UE's mobility within the long-term evaluation network, and the home subscriber server is the primary database for storing subscriber-related data in the LTE network. At the physical layer, these network components communicate using various wireless technologies such as the LTE and 5G, which utilize a range of frequency modulation schemes. The physical layer is responsible for converting digital data into analog signals that can be transmitted over the airwaves, and for receiving and decoding the signals back into the digital data.